On the second half of 4.3 about how derivatives shape a graph, we're specifically talking about the second derivative here. If you take a look at the objectives, we're going to determine the concavity and points of inflection of a graph. Now, both of these things are probably completely fresh ideas for you. So, of course, in a pre-calc class and in Algebra 2, you talked about where functions increasing and decreasing, relative mins and maxes, stuff like that. But concavity and points of inflection, this is going to be brand new stuff. And it's determined by the second derivative, all right? Speaking of the second derivative, look at the second objective to apply the second derivative test to find relative extrema. We already have a test to see where relative extrema, the local mins and maxes are. It's the first derivative test. Well, we have a secondary test is based on the second derivative, you would think, right? But it does the same thing. Where are your local minimums and maximums? All right, let's start off by taking a look at this warm-up exercise. Compare and contrast the graphs of f of x and g of x. So we're looking at both of these graphs. I can see that both of them are going upwards from left to right, which indicates that they're both increasing, right? Okay, so that's what they have in common. Both of these functions are increasing. But I do a visual inspection and I can see that they're not increasing in exactly the same way. So the one over here on the right, this g of x, when it's increasing, it seems to be slowing down, right? And yet this one over here on the right, this f of x, seems to be speeding up, right? So if I think about it, I'm talking about a rate of a rate. Increasing is about its slope, and if the slope is getting bigger, I'm talking about a second derivative here. So we say that this graph on the left-hand side, it's increasing, but it's increasing at an increasing rate. That's a second derivative. All right, the graph over here on the right-hand side, it's increasing again, just like the one on the left, but it's slowing down. It's increasing at a decreasing rate. Once again, we're talking about a second derivative. All right, let's look at this in comparison to the tangent lines. So in this next set of pictures, we're going to throw some tangent lines up in here. So let's zoom in here on this f of x graph. Look at where the tangent lines are. Tangent lines are appearing down below the graph here, right? And if I look at moving from left to right, I can see that these tangent lines are getting steeper, which again indicates that the rate at which it's increasing is also increasing. Let's look over here at the right-hand side, at the g of x function. Notice that its tangent lines are appearing above the graph. And if I compare these two tangent lines, I can see that it's getting less steep. It's starting to slow down. It's getting closer and closer to zero, horizontal tangent lines, right? Again, that's indicating that even though it's increasing at a decreasing rate. So the one on the left, it's going up, but the rate at which it's going up is also going up. And this one over here on the right-hand side, it's also going up, but the rate at which it's going up is going down. All right, so the graph on the left, it has a special name. It's concave up. The graph kind of curves upwards, right? And the graph over here on the right, g of x, this one is concave down. I can see that this shape looks like it's kind of caved downwards. So that brings us to our first objective here about being able to determine the concavity and points of inflection of the graph of a function. You can see Supergirl here, she's bending a crowbar, steel crowbar. You can see the strain here on her face. And the shape of the crowbar right now, as she's bending it, is concave down. So let's talk about some informal definitions of both types of concavity. The first one, a concave up. If you take a look at this pipe cleaner here, you can see that it curves upwards, shape of sort of like a parabola, right? So concave up just means that the graph curves upwards. Now, this is not a formal definition. The formal definition is going to be based on derivatives, the first derivative and the second derivative, specifically the first derivative, as we will see. But for right now, just to be able to do a visual inspection, we can point out that, hey, this graph looks like, if this is a graph, looks like it's concave upwards. All right, if I flip that thing, if I do a reflection across, say, the x-axis, got something that looks like a rainbow. Well, each one of these graphs is concave down, which informally just means that the shape of the graph is curving downwards. All right, so in the next couple of videos, we're going to refine this definition about what concavity means in terms of calculus, in terms of derivatives.